Okay. The last way I'm going to talk about the evolution of altruistic behavior is a concept called inclusive fitness, developed by William Hamilton and Robert Trivers. What we've been talking about is what's called direct fitness, which is ultimately measured by estimating individuals' chances of reproducing successfully. Indirect fitness results from the successful reproduction of relatives. An allele could become more common if it gives you a lower chance of probability, but increases the probability of your relatives reproducing, because your relatives also have that allele, because they're your relatives. Relatives, by definition, share a lot of alleles in common. So the sum of the two is inclusive fitness. That's the sum of direct fitness measured as the effect of an allele on an individual's chances of reproduction, plus indirect fitness, which is the effect of an allele, the effect that an allele has on the probability of the reproduction of relatives of individuals that have it. Okay, how does that work? Imagine you have a gene that causes individuals that have it to be altruistic to their relatives, to give up benefits so that their relatives may gain a benefit. Well, here's the thing, those relatives are probably carrying the same gene for the simple reason that that's the definition of a relative. Genetically, a relative is somebody that shares a lot of genes with you because they share a very recent common ancestor with you, right? You share a lot of genes with your siblings and a lot of genes with your parents, more than you would share with some rando off the street. So even if the altruist doesn't reproduce as much as he would otherwise, the altruism gene will make it will increase in frequency in the population if he makes it possible for his kin to reproduce. Yes?
So any mother that spends excessive resources in nurturing their young, would that be direct or indirect?
It'd be both. I mean, let's say you've got a population where some of the mothers have an allele that makes them want to devote themselves to their offspring, and others have an allele that makes them drop kick their offspring. The ones that drop kick their own offspring are not going to be, are not going to pass that gene on, and the ones that nurture their offspring will. In that case, it's a mix of both. But, if you think about something like, think about a brother that gives up benefits so that his sister can have a good life and ultimately can reproduce. That will be indirect. Yes. Okay. Hamilton's rule states that for altruistic behavior to be favored, you define something called the coefficient of relatedness, and that's the probability that any given allele is shared by two relatives. And it's also the average fraction of all alleles that two relatives share. Okay, I got half my genes from my mother and half from my father. So my coefficient of relatedness with both of them is 0.5. That means, first of all, that I have 50% of my genes came from mom and 50% from dad, right? It also means that for any given allele that I've got, there's a 50-50 chance that my mom will have it, and there's a 50-50 chance that my dad will have it. And it's transitive. Any given allele that my mom has, there's a 50-50 chance that she has passed it to me. Okay, yes? Okay? It turns out that the coefficient of relatedness among full siblings, among full brothers and full sisters, is also 0.5. Brothers and sisters, on average, share 50% of their genes. And if a brother has any given gene, there is a 0.5 probability that the sibling will have it. It's 0.25 for half brothers. It's also 0.25 for uncle or aunt and nephew or niece. It's 0.125 for first cousins, and so on. If you let B be the benefit to the recipient and C be the cost to the donor, then if the coefficient of relatedness times the benefit is greater than the cost to the donor, altruism will be favored. And the joke is that the British biologist, J.B.S. Haldane, was allegedly asked, would you give your life to save your drowning brother? And he said, no, but I would to save 2 brothers or 8 cousins. The joke is that Haldane would share half of his genes with each of his brothers. So if he's got an allele, there's a 50-50 chance that any brother of his has it. So if he has an allele that makes him give up his life to save 2 brothers, then that allele is going to persist in the population, right? Because at least one of the odds are very high that at least one of his brothers also has that allele. And the same is true, first cousins share an average of 1/8 of their genes. So if you save 8 cousins, it's statistically the same as saving yourself. This is not entirely meant to be taken seriously, but if you understand coefficients of relatedness, you get the point of the joke. Okay, duplicated some slides there. And the case study I'll give you is Belding's ground squirrel. This is native to mountain meadows of the western US and Canada. You can find them in places like the North Rim of the Grand Canyon. When they go out to the meadows to feed, they do it in groups. And some individuals, instead of feeding, will take turns on sentry duty, watching for predators. When they spot a predator, the sentry gives an alarm call. Sentry goes chirp, chirp, or something like that, and the group runs for cover. The reason this is altruistic is that the sentry, by giving the alarm call, has called attention to herself. And that means the sentry is almost 3 times more likely to be the target of the predator. The sentry is putting her own life at risk by being the one that gives the alarm call. You would think that if there's a gene for being a sneaky asshole, it would be favored in the ground squirrels, because ground squirrels that had it would spot the predator and then sneak away, and they'd survive and the predator would nab somebody else. How is that not the case? How does this altruistic behavior persist? Well, it turns out that there's a sex bias in who does the sentry duty. If every ground squirrel spent an equal amount of time as a sentry, adult females make up 40% of a typical group of ground squirrels, and they would give the alarm call 40% of the time. Right? If every member of that troop took turns, adult females would give the alarm call 40% of the time. Adult males make up about 25% of a family group, so they would give the call 25% of the time. 1-year females would give the call maybe 15% of the time, because 15% of the group is 1-year females, and so on. But when they observe who's actually doing the alarm calling, ooh, computer animation. Let's do that again. Ooh, spiffy, sophisticated. Adult females make up 40% of the troop, but they give about 65% of the alarm calls. 1-year females make up about 15% of the troop, but they give almost all the rest of the alarm calls. Males almost never do. The adult males make the alarm call maybe 5% of the time. Even the juveniles, the females give alarm calls more often than juvenile females call more often than juvenile males do. So the females are taking all of the risk, and the males are just, sitting back and not taking the risk. Why is this the case? Are ground squirrels just simply monstrously sexist? Right? Are the females doing all the work and the males are just saying, hey, make me a sandwich? Well, no. What happens is that in a colony, once males grow up, once they're weaned, they leave the colony that they're born in and they disperse to other colonies. Females, on the other hand, stay in the colony where they're born. The upshot is that a male ground squirrel in a colony is related to nobody except for maybe his own offspring. A female in the colony, however, is related to most of the members of her colony, because females stay in the colonies where they're born. The female is going to have sisters and mother and grandmothers and aunts and grandkids and nieces and nephews and grandnieces and grandnephews and second cousins twice removed and all of that stuff. The females are related to a lot of the members of their colonies. Males aren't related to most members of their colonies. So when a female gives an alarm call, she may be putting herself at risk, but she's saving the lives of a lot of ground squirrels that are all related to her. So if she's got a gene that influences her to be the one to give the alarm call, that gene is going to increase in frequency even if she gets eaten, even if she gets picked off by the predator. She has just saved a lot of individuals that are also carrying that gene. So the gene is going to increase in frequency. A male that gives the alarm call is putting himself at risk, but he's not saving the lives of many individuals that share his genes. Only his own offspring are going to be the ones that he's saving. So because females are relatives to many of their colonies and males generally aren't, a female might put herself at risk of death, but if she has genes that influence whether or not she gives the alarm call, those genes may still become more common if the fraction of her genes that she saves is greater than the fraction of genes that she personally carries. Right? That's what we mean by inclusive fitness. Females are actually more likely to give the alarm calls when their close relatives are nearby. They're smart enough that they can recognize kin. They look like they're kissing in this picture right there, but they seem to be using scent to recognize who their close kin are. So females will actually be more likely to give calls when they know that they have close relatives nearby. And that is inclusive fitness. Okay, I seem to have repeated a lot of these slides. Last case study, this is an East African bird called the white-fronted bee eater. And they've been studied since the late 80s by J.T. Emlin. That's how bee eaters live in the wild. That's a steep, muddy riverbank where they've dug out a bunch of holes. Every breeding pair claims a hole. They raise their young in there, and both parents have to go out and feed the hatchlings. And the problem is that space is very highly limited. There's not an indefinite amount of riverbank that they can dig holes into. So competition for holes is very fierce. It's a really tight real estate market. And on average, half the hatchlings, 48%, die before they mature, usually from starvation. Even with both parents feeding the offspring, it can be really hard for them to provide enough food for all of their offspring to survive. Okay. So what? Young bee eaters will often stay at their parents' nests, and they'll go out and find food. They do hunt bees, and they'll feed both their mothers and their younger siblings. Parents have actually been known to physically harass their older offspring to keep them from finding a mate. You know, this is the equivalent of mom saying, "Well, he looks nice, but has he got a steady job?" You know, there's this other guy who's going to med school. He's real smart. Maybe you should think about him. Yeah, in many species, parents will try to disrupt their offspring's mate choices. And it's certainly true in the bee eaters. Parents will harass their offspring until they give up trying to mate themselves. And young bee eaters that stay at the parents' nest will feed their parents, and they'll feed their younger siblings as well. And the effect is dramatic. Having one helper at the nest will double the chances of hatchling survival. All right. Hatchlings have a much greater chance of survival if they're being fed not by two parents, but by two parents and an older sister or brother. If you think about it, if you leave the nest and set out on your own, it's rough out there because there are not many holes and a lot of bee eaters that want them. So you're in pretty hard competition, and you might not be able to get a hole the first year that you're out of the nest. If you stay at home and you're a bee eater, you've got a place to live, and you are greatly increasing the chances of survival of your younger siblings who are carrying your genes as well. So if there is a gene that influences you to stay home and care for your younger siblings, even if you don't get to pass that gene on, your siblings will. Helper birds gain indirect fitness because they're raising their sibs or their half sibs sometimes. And they get a greater, come on, Wagner, sorry, caffeine's wearing off. They gain more fitness by assisting their parents than they would if they attempted to breed themselves. Now, they do eventually leave the nest and go out and try to raise their own young, but they're still giving up a chance to have their own babies. But they actually will pass more copies of their genes on by helping their parents raise their younger sibs than they would if they left the nest as soon as they could. Okay, did that make sense? So that is inclusive fitness right there. That altruistic behavior on the part of the bee eaters makes sense because birds that have it leave more copies of their gene in the population than birds that don't, because they're assisting relatives to breed. And that's actually a better bet than leaving immediately and trying to raise babies on their own. Okay, and I've got 12:12, so I'm going to bring up the lights, and I'm going to stop the recording.